Chapter 8 of History of Chemistry, Volume 2, by Sir Edward Thorp. This LibriVox recording is in the public domain. The Chemistry of Aromatic Compounds. The suggestions of Cooper and Kekulé that an explanation of the properties of chemical compounds could be sought in the nature and mutual affinities of their constituent elements rather than of their radicals were not wholly accepted at the time they were first made. Speculative ideas have to justify themselves by facts. The value of an hypothesis depends upon its usefulness and expediency, and on its power of indicating the lines of future inquiry. How far it is inductively sound and deductively useful is a matter for individual judgment. Consequently, the tendency to pass from purely rational and constitutional formulae to formulae which sought to symbolize the inner structure, the very skeleton, as it were, of a molecule, was resisted for a time, and by no one more strongly than Kolbe. Kolbe's attitude to the new doctrine may be said to have had its justification in his own work. His remarkable prediction, based on considerations which had nothing in common with Kekulé's doctrine, of the existence of the secondary and tertiary alcohols, so soon to be confirmed by Friedel's discovery of secondary propyl alcohol, and by Butenrau's isolation of tertiary butyl alcohol, served to retard the general adoption of Kekulé's views by showing that apparently they were no more fruitful in suggestiveness than those they were intended to supplant. But it was exactly in their suggestiveness with regard to the development of isomerism that structural formulae based upon valency were gradually found to be most useful. It was perceived that it was now possible not only to foretell the existence of isomers, but to determine their number, and to some extent to forecast their properties and modes of decomposition. Cayley, for example, calculated the number of possible isomers of the hydrocarbons of the generic formula carbon N, hydrogen 2N plus 2, and up to carbon 6, hydrogen 14, all those that theory predicted have been discovered. In no single case have more been obtained than the number indicated by theory. The accumulated weight of this and similar testimony ultimately established the doctrine of chemical structure on a firm basis. This conception received a great extension as the result of Kekulé's application of his ideas to the explanation of the chemical constitution of the group of substances of vegetable origin, consisting of essential oils, balsams, resins, and their products, which on account of their characteristic odors were collectively known to the older chemists as the aromatic compounds. Some of these, like oil of bitter almonds, gum benzoin, coumarin, oil of wintergreen, oil of anise, oil of cinnamon, oil of cumin, balsam of tolu, phenol, and certain of their derivatives, such as benzene, aniline, salicylic acid, cinnamic acid, toluene, cymene, had already been investigated with important theoretical results. But as a class they had received far less attention than the derivatives of the great group of homologous radicals of which methyl is the initial member. Of course, it was part of the doctrine of Liebig, the discoverer of benzoyl, that the aromatic compounds also contain specific radicals. But the relation of these compounds to those we now call aliphatic or fatty compounds was not understood, although certain analogies were recognized. In 1866, Kekulé drew attention to the following significant peculiarities of the aromatic compounds. 1. All aromatic compounds, even the simplest, are comparatively richer in carbon than the corresponding class of fatty or aliphatic compounds. 2. Among the aromatic substances, as among fatty compounds, numerous homologous compounds exist. 3. The simplest aromatic substances contain at least 6 atoms of carbon. 4. All decomposition products of aromatic substances show a certain family resemblance. The main product of the decomposition contains at least 6 atoms of carbon. For example, benzene, C6H6, phenol, C6H6O, etc., which would seem to indicate that all aromatic substances contain a nucleus or aromatic grouping containing 6 carbon atoms. Within this nucleus, the carbon atoms are in closer connection or denser combination, from which it follows that all aromatic compounds are comparatively rich in carbon. More carbon atoms can then be added to this nucleus according to the same laws that govern the fatty compounds. In this way, the existence of homologous compounds may be explained. On the assumption that carbon is tetravalent and that its valency is constant, Kekule showed how, by linking together 6 carbon atoms by alternate single and double bonds, 6 affinity units may be left free. If we assume that 6 carbon atoms are attached to one another according to this law of symmetry, we obtain a group which, regarded as an open chain, contains 8 unsaturated units of affinity. By making the further assumption that the 2 carbon atoms at the ends of the chain are linked together by 1 unit of affinity each, a closed chain, a symmetrical ring, is obtained, which now contains 6 unsaturated units of affinity. From this closed chain, all the substances usually designated as aromatic compounds are derived. In these, a common nucleus may be assumed. It is the closed chain C6A6, where A denotes an unsaturated affinity. The 6 affinities of this nucleus may be satisfied by 6 monovalent elements. They may also, wholly or in part, be satisfied by 1 affinity of polyvalent elements, the latter necessarily bringing with them other atoms into the compound, thus producing 1 or more side chains, which in their turn may be lengthened by the addition of other atoms. If each of the free units is satisfied by an atom of hydrogen, we obtain benzene, which, as Kekule demonstrated, becomes the center round which the great group of aromatic compounds might be said to revolve. Benzene was discovered by Faraday in 1825 among the volatile liquids condensed from the oil gas made by the Portable Gas Company. It had already played a notable part in the development of chemical theory in connection with the discovery of isomerism. It was now to play a far more important role, to become, in fact, the progenitor of a great family of substances, not only of theoretical value, but of great economic importance. The limits of this work preclude any attempt to trace in detail the development of the conception with which Kekule enriched science, or to dilate upon the great extension of benzenoid or cyclic chemistry which has resulted from it during the past 40 years. It has been said that Kekule's memoir on the benzene theory is the most brilliant piece of scientific prediction to be found in the whole range of organic chemistry. Of course, on its promulgation it had to run the gauntlet of criticism, and an army of eager, active workers was soon engaged in testing its sufficiency and in developing the rich province which it first made known. As the facts multiplied, other statical formulae were suggested by Dewar, Ladenburg, and Claus, but they have not proved more adequate to explain the facts as these have become better understood. Observations which seemed to contradict Kekule's theory, or which seemed to be imperfectly explained by it, have, in the light of fuller knowledge, been shown to be in harmony with it, and such additional proofs of agreement have thereby served to strengthen its position. Its capacity for development is, indeed, as in the case of every other hypothesis of the first rank, one of its cardinal qualities. It adequately explains the constitution of great numbers of derivatives whose analogies and relations apart from it would have remained obscure and in many cases unintelligible. The symmetrical distribution of the carbon and hydrogen atoms in the benzene molecule, assumed by Kekule on indirect grounds, has been established by the independent investigations of Ladenburg and others, and its ring structure has been demonstrated by Bayer and Perkin. Purely physical evidence, based upon its thermochemical and optical characters, can be adduced in its support. Determinations of the molecular volume and magnetic rotation of its compounds further serve to substantiate it. Friedrich August Kekule was born at Darmstadt on September 7, 1829. After passing through the gymnasium of his native town, he entered in 1847 the University of Gießen with the intention of becoming an architect. Attracted by Liebig's teaching, he turned to chemistry, and worked with will on amyl sulfuric acid and its salts. In 1851 he went to Paris, heard Dumas' lectures, and formed a friendship with Gerhardt, whose Traité de chimie organique largely molded his views. He became an assistant to von Planta, occupying himself with the chemistry of the alkaloids. Subsequently he came to London, worked under Stenhouse, and made the acquaintance of Williamson, then in the full vigor of his scientific activity. Here he discovered thioacetic acid. It was at this time also that his ideas with regard to structural chemistry began to take shape. Returning to Germany, he attached himself to the University of Heidelberg as a privat docent, and had for a pupil Bayer, who took up the study of the organo-arsenic compounds. In 1858 he published his memorable paper on the constitution and metamorphosis of chemical compounds and on the chemical nature of carbon, in which he developed his views on the linking of atoms, out of which has grown our system of constitutional formulae. The immediate result of this celebrated memoir was a call to the chemical chair of the University of Ghent, where Kekule had among other students Bayer, Hübner, Körner, Ladenburg, Linnemann, and Dewar. Here he remained 9 years, and here he published his classical Lehrbuch der organischen Chemie. The years he spent in Ghent were the most productive time of his career, and it was there that he developed his benzene theory, a conception as fruitful as that of his doctrine of atom linking. In 1867 Kekule was called to Bonn to take charge of the newly erected laboratory which Hofmann had designed. Although he continued to work, mostly in collaboration with his pupils, among whom may be named Anschutz, Berntzen, Thorpe, Carnot, Claisen, Dittmar, Franchemont, Van 't Hoff, Japp, Schultz, Wallach, and Zinke, his health after 1876 began to fail. He died on July 13, 1896. Of course, no statical formula can be the ultimate representation of the constitution of benzene. However convenient and suggestive such a formula may be, it can only be a transitional phase in its complete chemical and physical history. Kekule was early conscious of this fact, and suggested a dynamical hypothesis based upon a mechanical conception of valency. This he imagined might represent the number of contacts with other atoms which a vibrating atom experienced in the unit of time. 2 atoms of tetravalent carbon, each linked by one combining unit, will experience 4 oscillations, striking each other and 3 other atoms in the unit of time, while the monovalent hydrogen atom makes only 1 oscillation. The doubly linked carbon will collide with its neighboring atom twice, and also with 2 other atoms within the same period. The assumption that the carbon atom has a more rapid motion than the hydrogen atom is, however, not warranted by the kinetic theory. Other dynamic formulae have been proposed by Knorr and Colley. Colley and Bailey have further suggested that the absorption bands of benzene observed in the ultraviolet of its spectrum point to synchronous oscillations of its molecule due to dynamic changes in the making and breaking of the links between the several pairs of the carbon atoms, setting up vibrations in the benzene ring comparable with those of an elastic ring in the act of expanding and contracting. The large group of the essential oils containing hydrocarbons similar to oil of turpentine and classed under the generic term of terpenes might, from their origin and mode of occurrence, be expected to be allied in constitution to the aromatic compounds, and such is found to be the case. The terpenes are isomeric hydrocarbons of the formula C10H16. They are found sometimes singly, at other times mixed, in a great variety of plants, associated with the sesquiterpenes C15H24 and oxygenated substances such as camphor, borneol, menthol, etc., some of which have long been known and valued for their medicinal properties and technical applications. The elucidation of their constitution has taxed the skill of many workers during the past 30 years, but thanks to the labors of Wallach, Bayer, Perkin, Tiemann, Bredt, Compa, and others, an insight has been gained into their nature and analogies. They are apparently all cyclic compounds with certain attributes which connect them with hydrocarbons of the aliphatic series. Pinene, the characteristic constituent of oil of turpentine, obtained by distilling the resinous exudations of many species of pines, exists in 2 modifications, distinguished by differences in optical activity, known respectively as australine, found in American, Russian, and Swedish turpentine, and terebinthine, found mainly in French turpentine. It would seem from their empirical formulae, as well as from their association in nature, that the terpenes and camphor, which Dumas first showed to have the composition C10H16O, should be closely allied in constitution, and that it ought to be readily possible to effect their mutual transformation. The constitution of camphor was long one of the standing problems of organic chemistry, and dozens of formulae have been suggested at various times during the last 20 years in explanation of its structure. That it contained a benzene nucleus seemed to be proved by the ease with which it yielded toluene, cymene, and other benzene homologues. The first real insight into its structure was gained when Brett ascertained the constitution of camphoronic acid, C6H11, CO2H, and 4, a product, together with camphoric acid, of the oxidation of camphor, which he found broke up into trimethylsuccinic acid and isobutyric acid, and the structure of which was established by Perkin and J.F. Thorpe. The result of the Japanese monopoly has been to greatly enhance the price of natural camphor. During the last 10 years it has practically trebled. This has naturally stimulated endeavors to prepare this substance by synthetical means. Artificial camphor is now made from pinene by transforming the hydrocarbon into bornyl chloride by the action of hydrochloric acid. From this camphene is prepared. By treatment with glacial acetic acid it forms isobornyl acetate. On hydrolysis this is transformed into isoborneol, which by oxidation yields camphor, differing from the naturally occurring variety only in the fact that it is optically inactive. All so-called aromatic compounds are not necessarily cyclic systems, for it has been recognized within the past few years that some of the most valuable natural perfumes, such as that of the rose, lavender, and orange blossom, lemongrass, geranium, ylang-ylang, neroli, etc., owe their characteristic aroma to the presence of terpenes and camphors, which are not strictly benzenoid or cyclic compounds, but ruptured rings behaving like open chain or aliphatic substances. To judge from past experience, it may be confidently stated that, now the constitution of these substances is understood, their synthetical preparation on an industrial scale is practicable. The discovery by Cahors in 1844 that oil of wintergreen is substantially methylsalicylate led to its artificial production from synthetically prepared salicylic acid. Sir William Perkin in 1868 effected the synthesis of coumarin, the aromatic principle in woodruff and hay. Fiddick in Milch in 1869 synthesized helotropin, and in 1871 Tiemann and Harman obtained vanillin, the characteristic aromatic body in the vanillapod, by synthetic means, and established its manufacture on a commercial scale. The chemical nature of the characteristic odoriferous substances in oil of cumin, anise, rue, cinnamon, heliotrope, jasmine, violet, parsley, etc., has now been established, and some of them are made industrially. The artificial essence of violets, known as ionone, prepared by Tiemann in 1893 and now made commercially, is similar but not identical in structure with the true perfume, Irone. What is known as artificial musk is a trinitrobutyl toluol. Artificial orange flower oil is a methyl ester of anthranilic acid. In Volume I a short account has been given of the early history of the large and important group of vegetable products known as the alkaloids. Many of these have long been valued on account of their powerful physiological action. As they all contain nitrogen and are generally basic, they were regarded by Berzelius and subsequently by Liebig and Hofmann as akin to ammonia in constitution, and were classed as amines. The first experimental evidence of their nature was obtained by Gerhardt, who found that, when strychnine and certain of the alkaloids belonging to the quinine group are treated with potash, an oil was obtained which he termed quinoline, and which was recognized by Hofmann as identical with a substance obtained in 1834 from coal tar by Runge, and at that time known as leucol. By other modes of treatment certain alkaloids, namely nicotine and conine, were found to yield pyridine, a basic substance found by Anderson in 1846 in the fetid liquor obtained by distilling bones, and since found in coal tar. Others of them, for example, papaverine, nicotine, etc., yield isoquinoline, an oil also discovered in coal tar by Hugwerf and Van Dorp in 1885. These three substances, quinoline, isoquinoline, and pyridine, constitute so many nuclei in the constitution of a large number of alkaloids. Pyridine resembles benzene in being a cyclic compound consisting of 5 carbon atoms and 1 nitrogen atom. Quinoline stands to pyridine in much the same relation that naphthalene stands to benzene. It can be obtained synthetically, as first shown by Koenigs and Scropp, and subsequently by Dubner and von Miller, from benzene derivatives. Isoquinoline, isomeric with quinoline, differs from that substance in the position of the nitrogen atom. It too has been synthetically prepared from benzene derivatives in a number of ways. Among the naturally occurring pyridine alkaloids may be named piperine, found in black pepper, and conine, the poisonous principle of hemlock, Conium maculatum. The latter alkaloid was prepared synthetically by Ladenburg in 1886. As first obtained, it differed from the naturally occurring product, which is dextrorotary, in being optically inactive. Ladenburg surmised that the synthetic preparation stood to the naturally occurring compound in the same relation that racemic acid stood to tartaric acid, and that by treatment in the manner employed by Pasteur, the racemic modification of conine might be separated into its dextro and levo constituents. This was found to be the case, but the separated dextro component was now found to be distinctly more optically active than the pure natural variety. It was in fact an isomeric modification, isoconine. By heating this to 300 degrees, it was transformed into ordinary conine, identical in all respects with the natural alkaloid. Ladenburg has also effected the synthesis of piperine by condensing piperidine and piperinic acid. Nicotine, the alkaloid of tobacco, was discovered by Posselt and Riemann in 1828. Its constitution was first ascertained by Pinner, and it was synthetically obtained by Aimé Pictet in 1904 as an inactive substance capable of being resolved by the crystallization of its tartrates into a dextro and levo modification, the latter of which was identical with that found in the tobacco leaf. Atropine and hyoscyamine, the poisonous principles of belladonna and henbane, are isomeric alkaloids, the former of which is optically inactive and the latter is levorotary. Atropine is in fact the racemic modification. The constitution of both alkaloids is known, and their synthesis is now possible. The successive steps may be thus indicated. 1. Synthesis of glycerin. Faraday, Kolbe, Melsens, Boerhaave, Friedel, and Silva. 2. Glycerin to glutaric acid. Berthold and De Luca, Cahors and Hoffmann, Erlenmeyer, Lermontov, and Markovnikov. 3. Glutaric acid to suberon. Brown and Walker, Bossingalt. 4. Suberon to tropidine. Willstatter. 5. Tropidine to tropine. Willstatter, Ladenburg. Synthesis of tropic acid. Berthold, Fiddick and Tollens, Friedel, Ladenburg, and Rugheimer. 7. Tropine and tropic acid. Atropine. Ladenburg. The alkaloid cocaine, contained in the leaves of Erythroxone coca and now employed as a local anesthetic, was discovered by Niemann in 1860. It has been shown to be closely related to atropine in constitution and has now been synthetically prepared in the dextro modification. The alkaloids papaverine, narcotine, narceine, contained in opium, are derivatives of isoquinoline, as also is berberine, found in the common barberry, Berberis vulgaris. Papaverine, which occurs in opium to the extent of about 1%, was first isolated by Merck in 1848. Its constitution has been established by Goldschmidt. Narcotine is, next to morphine, the most abundant constituent of opium. The study of the products of its hydrolysis and oxidation, namely opianic acid and codernine, both of which substances have long been known, has indicated its probable structure. Narceine is closely allied to narcotine, and can indeed be obtained from it by combining the latter alkaloid with methyl iodide and treating the compound with caustic potash. The constitution of berberine, which is one of the few colored vegeto-alkaloids known, has been worked out by Perkin. As yet, nothing definite is known concerning the structure of the most important and largest constituent of opium, namely morphine, or of its congeners codeine and thebaine. Grimaud, however, in 1881, converted morphine into codeine by treatment with methyl iodide and potash, Hence the two alkaloids stand in a relation somewhat similar to that in which narcene stands to narcotine. There is very little doubt that the three alkaloids are very closely related, and that a knowledge of the constitution of one of them would immediately elucidate the structure of the others. They are probably phenanthrene derivatives. Quinine and chinconine, the most important of the cinchona alkaloids, are quinoline compounds, and are closely related in constitution, but the many attempts to unravel their structure have yielded no definite results up to the present. End of chapter 8.